Okay, let's get started. So we're going to continue talking about virtual memory, and then we're going to dive into caching and translation look-aside buffers. Hopefully we'll get to TLBs. Okay, so remember that with general address translation, the CPU, the processor, and what the process sees is virtual addresses. And then it's the job of the memory management unit, or MMU, to translate those into physical addresses, which is how we actually access memory. Now, we can also have untranslated reads and writes. So there are two views of memory, right? There's the view of memory that the processor has, and then there's the view from memory of actual physical addresses. And this translation box is what converts between the two. So if you think about translation, it makes it a lot easier for us to implement protection, right? If one process can't see other processes' memory, can't see the operating system's memory, then implicitly we're protecting those processes from that process, and we're protecting the operating system from that process. Okay, now there's another benefit, which is if we've decoupled what one process sees as its view of memory from all other processes, then we can let every process have the same view of memory. So memory that starts in a virtual address space at 0 and goes to 2 to the 31st minus 1. Okay, so remember from last time we had the multi-segment model where we have a segment map that gets stored in the processor, and the segment map just contains a set of base and limit pairs. So here we have 8 of them, and we take our virtual address divided up into 2 fields. One field is the segment number that we use to index into that table. That gives us a base. We add our offset, and that gives us the physical address that we're going to use. We have to perform some checks. We have to make sure we didn't run off the end of the table. We also have to make sure that the size of the region is greater than the offset. Now, we can also, here I have the segment number encoded into the virtual address. It can also be coded into the instruction. So for example, in x86, here we have a move, and we're going to use the ES, or extra segment, with the address being the BX register. We're going to move the contents of memory at that location into AX. We also need some metadata here. We're going to, over the next few lectures, really look at what that metadata is. Right now, in this case, it's just a valid and not valid bit. But it could also be permission bits like read, write, read or read write, or execute only, or whatever. Okay, so the question is, does translation save us from copying 100 copies of the same program? So to a certain extent, yes, right? We could have one shared code segment for everyone who's running the IDE. And that would just be marked as, say, execute only, and could be mapped to the same, let's say, base 0 register, right? So the same 0 segment, rather. Right? And so then the code would appear in everybody's virtual address space at the same location. All right. Now, what do we do if we're in a situation where not all of the segments will fit in memory, either for an individual program or for a set of programs? Well, we can do an extreme form of context switching. Right? So if you think about it, like in this case, when we context switch, what do we have to do? We have to save this segment map out and load the new segment map. Right? That will change the processor's view of memory to be that for the new process. Same thing, we have to load unload all the CPU registers for the old process, load all the CPU registers for the new process. Well, an extreme form of this would say, if everything doesn't fit into memory, then we just swap out segments from memory out to disk. So when we're going to run process P1, we load its segments into memory and unload process P0 out to disk. Now that seems extremely slow and kind of unreasonable, but that was actually the approach that was used on many early computers because we didn't have enough physical memory and we wanted to do multi-programming. So we paid the price with very, very expensive context switches. Okay, so what might be a better alternative? Well, if you think about it, programs spend most of their time in a relatively small amount of their code for most programs, not all, but for many programs, if you look at like what are the hotspots, the active regions of a program, they're much smaller. Now, with this segment model, we either have to have an entire segment in memory or an entire segment out on disk. We can't have both. Right? There's no way to say, well, I just want this part of the segment to be in memory and this part you can put out to disk. So we want finer granularity of control. We just keep those parts of a segment in memory that are actually being used, and everything else we can leave out on the disk and pay a really expensive cost if we actually go and access it. Okay, so if we look at segmentation, some of the problems that we run into are like these variable sized chunks that we have to fit into memory. We play Tetris with memory. As programs start and finish, we're going to end up with different size holes based on the size of their segments in memory. Now, when new processes come along and we're trying to fit their segments into memory, we may have to do a lot of copying around and move things around. So that gets very expensive. Same thing with if we want to grow a segment, we might have to shuffle things around. So lots of moving around. We also have these limited options for swapping to disk in that we can only swap at the granularity of an entire segment. And if segments are large, that's a lot of data to copy out. And if it contains some regions that are active, we're then going to turn around and copy it back into memory. So we have two different types of fragmentation issues. So one is external fragmentation. Those are the gaps that are created between segments. And our solution there is we have to move things around. The other is that segments may grow over time, but they don't shrink. And so we end up with internal fragmentation where, say, we've allocated a stack segment that's 64 kilobytes, but we're only actually using 16 kilobytes of that 64. So that other 48 is just wasted space. Nobody can use it. So we need something that's better. And if we think about what we want to do, right, what we want to do is we have this view of memory from a process's virtual address space, here program 1 and program 2, and we're using the translation map to convert that into what are the physical addresses and the physical layout of memory. And here I've done a segment-like model, right? There's a code region in virtual address space, and that maps to a contiguous code region in physical memory. But this is just a map function. And so we could map any virtual address to any other physical address. So there's no need for this to be all nice contiguous regions. And that would give us a lot more flexibility. And so really the question is like, what's the right granularity, right? Is it down to the individual byte? The translation map maps individual bytes of the address space to given locations. Or is it at the granularity of segments? Well, we saw there's a bunch of issues with segments, so we know we want something smaller. We probably don't want it down at the granularity of bytes because that would make the complexity of these translation maps really, really high. Right? We'd have more bookkeeping information than we'd actually have, memory in use. So that brings us to paging, which is we're going to think about organizing our physical memory into fixed-sized uniform chunks. So instead of allocating memory in these variable-size, segment-sized chunks, we're going to allocate them in pages. Now, if you think about it, if I allocate with pages, how can I determine whether a given chunk of memory is free or allocated? Well, if they're fixed sizes, I can just use a bit vector. And in that bit vector, if there's a 0, it means that page is free. If there's a 1, it means it's been allocated to some process. So now when I need to find a free page to give it to a process because it wants some memory, I just scan quickly through that bit vector. As soon as I hit a 0, I allocate it. Now, an important thing to think about is that every page in memory is equivalent. It takes the exact same amount of time to read or write any page in memory. So it doesn't matter if I allocate 2 pages contiguously or I allocate them at opposite ends of memory. The access time is the same. All right, so now we really can think about this translation map. It's just mapping any virtual page to any physical page. Okay, now how big do we make those pages? I kind of alluded to it, right? We don't want to make it so small that the bookkeeping overhead exceeds the size of our pages. But we don't make it as large as segments, because if we make it really large, we'll end up with a lot of internal fragmentation. Right? If we had 4 megabyte size pages and we have 64 kilobyte size stacks, then that page allocated to the stack is mostly going to be wasted. And again, memory in this case, physical memory is precious. So not as big, but not too small. And so over time, people have evolved. And typical sizes today are about 1 kilobyte to 4 kilobytes, or even 16 kilobytes in size. Some architectures include support for much larger page sizes, where we know we have physical objects that are going to be very large. And we'll touch on that later on. So now if we think about it, to represent the sort of same information that we were storing in a segment, we potentially are going to need a lot of pages. Right? It's not going to be like, before we just had one segment, we had 8 segments, so we'll just have 8 pages to represent our program. We might have many, many more, hundreds more of pages than we had segments, or even more. Okay, so how do we implement simple paging? So we're going to start with the very simplest way we can do it, which is in the processor, we're going to have a page table pointer. That page table pointer will point to a location in physical memory that contains a table. And that table just consists of a combination of physical page numbers and permission bits. All right, so now we're going to take our virtual address, and again, we're going to split it into 2 fields. So there's going to be an offset field, which will be the offset into a page of the data that we're trying to retrieve. Now, since it's into a page, and we're dealing with things on page granularity, we can just copy that offset over into our physical address. So there's no addition that we have to do like with segments, right? Because we don't know where a segment starts in physical memory. That's why we had to increment that start point, that base, with our offset. Here we know the boundaries of pages are uniform. And so it's just the offset from the start of a page. Okay, so for example, if we have a 10-bit offset, that gives us pages that are 1,024 bytes in size. If we have a 12-bit offset, how big are our pages going to be? Yeah, 4,096. Okay, you're going to learn powers of 2 if you didn't learn them already. Okay, so now we're going to take the rest of our address, the virtual page number, and that's just an index into our table here. So we index into the table, that gives us the physical page number. We combine that with the offset, and we get the physical address. Now, of course, we always have to do lots of checking. I'll say it again, don't forget to do checking. It might show up on the midterm or something like that. You want to make sure that the entry that is being referenced is actually valid. Both it's a valid entry and also for the access mode that the processor is using. Okay, so like for example, this page here is a read-only page. So we want to make sure that the access is like an instruction fetch or a load and not a store. Okay, so we check the permission bits. If they don't match, like you're trying to write to this page, that would generate a fault. Or if the page is invalid, or if you're run off the end of the page table. So we also have to look at the virtual page number versus the page table size. So 2 registers that we're going to store in the processor, the page table pointer and the page table size. Okay, so the rest of the bits of our address, our virtual address, is going to be our virtual page number. So if we had a 32-bit address, it would be 10 bits for our page, and then the remaining 22 bits would be used for our virtual page number. And 2 to the 22 is roughly 4 million. So we could have up to 4 million, roughly 4 million entries in our page table. Okay, questions? Yes? So the question is, given a physical address, how do we know if that physical address represents data that's in memory or maybe out on disk? So that's where the metadata and the bookkeeping will come into play. So for example, if it was out on disk, we might mark that entry as invalid. So now if I try to reference it, what's going to happen? I'm going to page fault, right? Because I tried to access something that's marked as invalid. Now the operating system checks its books and realizes, oh, that page is actually out on disk. And so it'll have to fetch it into disk and then put it someplace, update the page table entry with the actual physical page number of where it put it, and then set the bit to valid, and then it'll restart the instruction. Okay, so let's go through a really simple example. So we're going to have 4-byte pages, and here's our virtual memory. We got 3 pages in our virtual memory. We've got a page table with 3 entries, and here's our physical memory. Okay, 4-byte pages. How many bits do we need to represent that for our offset? 2. 2 to the 2 is 4. Okay, so the rest of our address will be our virtual page number. So if we look at address 0, right, that's going to be virtual page number 0. And so that's going to be, if we look in our page table, we'll see it's at physical page 4, which will write everything out in binary. That's 100. And so here it is at 10 hex in physical memory. Similarly, if we look at our next one, so where is 4 hex located? That's 0100. So offsets 0, page is 1. That maps to 3, which is 11. And so that maps to Charlie hex. And finally, if we look at 8 hex, that's going to be 10000, 2 to the 3. And then that'll be page 2. And that's 1, so that's going to be up down here, or rather up here at 4 hex. So 100. All right? Okay, that's the simple. Now let's actually look at some offsets. So what if I give you address 6? What does that map to? So all we're going to do is we're just going to write it out in binary. So if we write it out in binary, we'll see that it is 0110. So our offset is 10. So we copy that over to our physical address. And it's on page 1. And page 1 is 3 or 11. So we're going to end up with 1110. Right? Which in hex is 0e hex. Right? We can do one more. We'll do, let's do 9. So where does 9 hex lie? So again, we'll convert 9 hex into binary. So that's going to be 1001. So offset is 1, and page is 10 or 2. So there's page 2, that's 1, so it's going to be 101 or 5 hex. Okay? So again, when we're doing paging, copy over the offset, look up the virtual page number, check the permission bits, combine the physical page number, and you get your target address. All right? Now there was a question about sharing in the chat. So how do we do sharing with pages? Well, it's actually very easy. So here is one process, process A's page table, and it's associated with a page table pointer. If we want to share a particular page, like let's say we want to share page 2, we just simply add that same entry into that second page processes page table. All right? Now a caveat here. So they're both, the same physical page will appear in both processes. But does it appear in the same place? No, right? In one, it's virtual page 2. In the other, it's virtual page 4. What might be the implications of that, a potential problem? Yeah. Exactly. Yeah, so we'll have different virtual addresses that are pointing to the same physical addresses, which means if we have objects that say process A creates that have pointers and things like that, those virtual addresses for those pointers won't work when we look at it from process B's point of view. So we can share, basically we can share, just values and things like that. But if we wanted to share objects, we'd want to make sure that we map them both, say, in page 2, or we map them both in virtual page 4 so that the virtual addresses were the same, mapping to the same physical addresses. And that way, if I had a tree or something like that, the pointers would all work. Otherwise, they won't work. Okay, so that's a little caveat that you just have to worry about if you're going to map the same page into different address spaces. So the question in chat is, does this mean both processes can modify the same address? They can both modify the same physical address with different virtual addresses. And they can read the same physical address with different virtual addresses. The question is, when we do swapping, do we just swap the page or the whole segment in which the page is located? So here we can swap on the granularity of an individual page. So an individual page could live in physical memory or it could live out on disk. Whereas with segments, it was the entire segment lived in memory or the entire segment lived out on disk. So now you can kind of think, how we can use this to our advantage. If most of the pages in our address space aren't really being used actively, they don't need to be in memory. They can be out on disk. And that frees up physical memory, which is expensive, for other processes. So we can now fit more processes, active portions, into memory. Okay, so where do we use sharing of pages? Well, we can map the kernel region of a process to have the same operating system kernel code and data structures across all processes. And this is nice because now it means that when we go into kernel mode, the operating system can access all of its code and data, and it can access the processes' code and data. And so it doesn't have to do any translation. The translation is done for the kernel. Now, of course, we have to make sure that when we're in user mode, we can't access that portion of the page table. Okay, we can also have, as first question we got today, we can also have different processes that are using the same binary. We just map the pages for the code into the physical pages for the code into all of the processes running that binary. Mark it execute only, and that way nobody can modify it. Okay, we can also use it for user level libraries, system libraries. So only one copy of libc needs to be loaded, not multiple copies. Again, we mark it execute only so that we don't have to worry about anybody modifying it. And then we can also, as we talked about earlier, have shared memory between processes. The two processes that can see the same set of data, if we put it at the same place in the virtual address space, they can share objects. So if you think about it, it's like very similar to the sharing that we have between threads. Right? It doesn't require any context switches into the kernel to do communication between two processes. I just read and write memory, and other processes that are sharing that same memory can see my reads and my writes. So that's a good thing. It's also a bad thing because obviously we're going to need things like synchronization and all of those sorts of things to make sure that everybody sees consistent views of data structures we modify. All right. So remember the layout that we had for memory. We have the kernel getting mapped into every single address space. Again, this gives us the advantage of the kernel can copy to and from its buffers, from user buffers, and have all the translation be done in hardware. We have our stack, we have our memory, we have our heap, we have our code, our initialized and our uninitialized data segments. Now, some of the security things that we do, and it might be a little hard to read this on the slide as it's projected, but the start of our stack starts somewhere randomly offset from 2 to the 31st minus 1. Similarly, our heap starts at some random offset, and our code can start at some random offset from 0. And we do that as part of address space randomization. So to make it harder for an attacker to guess where a particular data structure might be located in memory, or where a return address might be located on the stack, or local variables in the stack frame are located, we do this randomization. That way, if someone's doing some kind of buffer overflow or code injection attack, they're not able to know directly where a particular routine might be loaded or where a particular data value might be. The caveat here is if you operate with a 32-bit machine, it's only 4 gigabytes, and the amount of randomization you can do is going to be limited. And so if I have enough ability to probe, I can usually guess where things are located. On a 64-bit machine, that's not an issue because it's very hard to try and guess where something might be randomly placed in a 64-bit address space. Okay, another thing is because of Meltdown, we realized that user programs could figure out what kernel data structures contained, especially security-sensitive ones. And so now what we do is we actually don't map the entire kernel into all address spaces. So those sensitive things get mapped into a separate kernel address space, and we only map things like buffers for copying to and from the kernel and simple code routines into the process's address space. So that protects the kernel from these kinds of observation attacks, but it comes at a cost. Now when the kernel wants to access that code or access that data, it has to do it has to switch the context for the address space, and that's expensive. We'll see why, when we get into caching and TLBs. Okay, so to summarize what we get with paging. So we're able to now take that view of the virtual address space, and through the page table, we can map it to any physical memory view that we want on a page granularity. Now here, I've just used the same sort of model as we had with segments, right? So contiguous regions in our virtual address space happen to map to contiguous regions in our physical address space. But that's not a requirement, right? If our stack here grows down, if we look over here in physical memory, there isn't enough space for those 2 additional page frames we need. But that's fine, because every page in memory physical memory is equal. So we can put those 2 stack frames anywhere we want. So I might choose to, let's say, put them there. Or I could put one here and put another one down here, or anywhere else. It doesn't matter. There's no benefit that we gain from making them be contiguous. And because of that, we get a lot of flexibility in how we can place things in memory. We now don't have to worry about external fragmentation. We're not going to ever have to move things around to make room for another process. The only thing we might do is we might take 1 or more pages and copy them out to disk to free up memory so that we can allocate memory to another process. But we're not going to do random moving around within memory. Okay, but there's some challenges. Look at this table in the middle, right, which maps all of our virtual addresses, or virtual pages rather, to physical pages. And what do you notice? It's got a lot of empty spots, right? And you also notice that the size of the table is proportional to the number of pages in our virtual address space. So we've got a table that's mostly empty that's really large. So that, of course, you can ask the question, well, just how big do things get? Well, if we had a 32-bit address space, right, that allows us to have 4 gigabytes, and we use a typical page size of 4 kilobytes, how many bits do we need for our offset? 12. 2 to the 12 is 4,096. And so how many bits are we going to end up for our virtual page numbers? We end up with 20. Right? So those 20 bits translates into a page table, each of which entry was about a word. So we're going to have 4 megabytes for our page table. So 4 megabytes of physical memory where, again, if we look back here, it's mostly empty. So that's not very efficient, right? What about a 64-bit machine? Well, if you think about it, okay, a 64-bit, 2 to the 64 divided by 2 to the 12, how many virtual pages are we going to have? is 2 to the 52nd virtual pages, or what is that, 4.5 exa entries, each of which is going to be 8 bytes in size, so we're going to need 36 times 10 to the 15 bytes of physical memory just to store the page table. So clearly that's not going to work as an approach. Right? We're going to have more memory taken up with the bookkeeping than actually used by the program. And so that's just not going to work. Okay. So the problem we have here is our address space is sparse, and yet with the single table that we have, we need to keep track of every single entry. So what if instead we had a way of trying to keep track of just the entries that were likely to be in use? How could we do that? That's what we'll get to in just a moment. Oh, so there was a question, why do we need to map some kernel space into user space? Isn't the user never able to access things in the kernel space? Yes, that's correct. So the user can never access kernel space. The reason why we map things into, go back to it. So the reason why we map this kernel space into the process space is that when you go from user mode to kernel mode, and the kernel, let's say you want to write something to a file. So you provide the kernel with a buffer. That buffer could be spread across many different pages depending on how your virtual address space maps those pages to physical pages. By being able to use the processes process map, its page table, the kernel can just simply say, oh, just copy in virtual address space this buffer for this number of bytes into a buffer in kernel space, since the kernel space is mapped into the process's page table. So it makes that really convenient. Otherwise, if you were in kernel space, you'd then have to manually kind of walk the page table and translate all of the addresses in order to do that copying. So this makes it much easier, lets us use the hardware to do that, and we use protection to make sure that the user process can't access the kernel data structures or code. Okay, so some discussion. So what do we need to switch on a context switch? Well, we just need to switch the page table pointer and the limit. Those are the only things that we need to save. Yeah, question? Yeah, so the question is if we're in kernel mode and we want to access the memory of another process from one process, then typically what you would do is you would copy from the source process into a kernel buffer, then change the page table to point to the new process. Now you're going to have its translations. You then copy from that same buffer. Again, this is why you map the kernel into all of the processes, into that process's buffer. All right, so that would be an example of inter-process communication. So I do like a Unix pipe or something like that, and that's going to copy from one process's address space into another. But it's mediated by the kernel, and so I have to do a system call into the kernel in order to do that. That's why being able to map a page of memory into multiple processes is really nice, because then I'm just reading and writing directly to that page. The kernel isn't getting involved in copying the data. And in fact, there is no copying. You just copy it into that page. No additional copying, I should say. Okay. What provides the protection for us? Well, we get protection through translation, right? The page table entries limit what you can actually access, right? If there's no virtual to physical mapping that lets you access another process's memory or the kernel's memory, then you can't access them. You can only generate physical addresses that correspond to mappings in your table. We use dual mode operation to keep the user from modifying that table. So only the kernel gets to modify the table. All right, so what are some of the advantages here? Well, we get really simple memory allocation. Right? We just use a bit vector to tell us this page is in use, that page is not in use. So we can just scan right through and find a free page really quickly. It's really easy to do sharing. Right? We just map the same page into multiple address spaces. But what are some of the disadvantages? Well, our address spaces oftentimes are sparse. And so we end up with these really huge tables that could be larger than the actual data that we're actually trying to, for our code, data, heap, stack, and everything else. So that's a problem. Another problem is that not all the pages are being used at any given time. And we want to really kind of think about just keeping in memory those pages that are being used and letting the rest of the pages live out on disk. We need some mechanism for doing that in the context of page tables. All right, so this simple page table is just too big. So this is not an approach that we can use unless we're going to go to like maybe really large pages, and then we'd end up with tremendous amount of internal fragmentation. So what if we had some kind of multi-level scheme, right, where we had multiple levels of page tables, like a tree of page tables or a tree with segments and pages? Let's look at what that might look like. So if we think first about what a page table is kind of providing for us, right, it's just a map that maps from some virtual page number to a given physical page number that we've allocated for that page. So we take a virtual address, give it to the page table, and the page table returns the associated physical address. And so really it's just a lookup table, a really large lookup table, but there are lots of different ways that we can implement a lookup table. And so we can use those to try and do something that's more efficient than just having a giant linear table that takes up a ton of contiguous memory, physical memory also. Okay, so what are some of the other structures we might be able to use here? I kind of gave one away, which is maybe a tree. We could also use something like a hash table. Right? All we need is just some mapping function that we give it a virtual page number and it returns a physical page number. That's all. All right, so let's look at one potential fix, which is a two-level page table. Okay, so we're going to have a tree of page tables, and we're going to take our virtual address, and we're going to divide it up in kind of a magical way. So we're going to take 12 bits and use that for our page size. 12 bits is 4,096 bytes. All right, so that takes away 12 bits out of our 32-bit address. That leaves us with 20 bits. We're going to divide that evenly and have 10 bits for our top level page table and 10 bits for our next level of page tables. Each page table entry is going to be 4 bytes in size. All right, how big is our page? 4 kilobytes. How big is our page table entry? 4 bytes. How many entries do we have per page? 1024. How many bits do we need to index into 1024? 2 to the 10, or 10 bits. So that's where our magic 10 comes from, right? If you think about it, this page here contains the entire page table for that level. So a page table for a level is 4,096 bytes divided into 4-byte entries, 1,024 of those entries indexed with 10 bits. That's why this is kind of a magic breakdown of a 32-bit number. Okay, so we have a page table pointer, which we store in the processor. We don't need a page table size pointer. Why? It's fixed size, right? It's limited by the size of this page and the fact that the size of that page contains all 2 to the 10 entries. So we just need one pointer. And we're going to take our top level, top 10 bits, index into our root of our page table. And that is going to give us the physical page number of our next level page table. All right, so that's this physical page here. All right, and then we will, so I should point out, when we do a context switch, the only thing we have to save is this page table pointer. On x86, it's the CR3 register. Okay, so we're going to take our next 10 bits and use that as an index into this page table, and it's going to give us the physical page number of the page in memory. We then combine that with our offset, and that gives us the physical page and the actual offset on that page. All right? Now, we also need to have valid bits on all of these entries, because now we don't have a length. So, it might be that we're only using the first, I don't know, 500 entries in our top level page table. So we need valid bits to tell us whether some entries are valid or invalid. We don't need every one of these second level page tables, right? If the entry here is invalid in the top level table, then there's going to be no associated second level table. So now we only really need to map those regions of the virtual address space that are in use. If it's not in use, we don't need to have a second level table associated with it. So for our sparse address spaces, this is going to be really good, because we've now drastically reduced the number of these second level tables that we need. The other thing is, while we keep our top level table in memory, these second level tables can actually live out on disk if they're not being used. And again, we just need to do some bookkeeping in this top level table to tell us, oh, hey, I put this second level table out on disk. It's not actually the case that it's invalid, it's just out on disk. All right? So we get a lot more flexibility. Now we can just keep the page tables in memory that are actually being used, and the ones that are actually active stay in memory. The ones that aren't as active go out to disk. Okay. So here's an example of 32-bit address translation on x86. Their terminology is the top-level directory is called a page directory, and it has page directory entries, PDEs, instead of PTEs. And this base register, CR3, provides the physical address of that page directory. We take our top bits, we use that as an index into that to get our PDE. That gives us the physical page number of our page table, our second level table. We use the next 10 bits to index into that. That gives us our physical 4K page, and we use our offset to get the physical address. All right, so when we context switch, we just save out the CR3 from the old process, load the CR3 from the new process, and now we get a different page directory. Yes, question? Okay, so he's the guy I asked to be in the audience so he could ask the question that set me up for the next slide. So the reason why we need lots of bits in the page table is because what do we need? Right? We need to know what's the pointer to the next level of the page table, or what's the pointer to the physical page. That's not a lot of bits, right? So what else are we doing? We have permission bits, right? So we need to keep track of, is this valid? Is it invalid? Is it read-write? Is it read-only? Is it execute-only? Is it out on disk? When was it last accessed? Is it clean, dirty? There's lots and lots of information that we're going to store in the page table entry. And so that's the answer to why it's 4 bytes. So you can see here, for example, there's some free bits. These are allocatable to the operating system. The operating system can use these bits for bookkeeping. So it could use these bits to say, oh, this page is actually out on disk. And so use the other bits in the PTE to figure out where it's on disk. Like maybe it's the logical block number of the disk block that contains the page table. All right, but there's a lot of other things. So, valid, writable, has it been accessed recently? When we get into paging, that's something that we'll use to say, this is a page that's been accessed recently, so it's active, as opposed to a page that has not been accessed recently, and so, does it really need to live in memory? Maybe it could live out on disk. There's other bits like, is it dirty? So has it been modified? Has it been written recently? And that's going to be important because if we wanted to say, evict this page from memory, it means we'd actually have to copy it to disk. Okay, and there are other bits that are, architecturally dependent. Okay, so how do we use the PTE? Right, as I said, right, an invalid page table entry could mean multiple things. It could mean that, yeah, really, this is invalid and your program stepped in this location, it's a landmine, and we're just gonna seg fault and terminate your program, right? Or it could mean, the page or the directory is just somewhere else. It's not in memory, it's out on disk. So we check the validity, and then we use those other bits to figure out, hey, where is it located on disk if it's not in memory? So demand paging is where we're only going to keep the active pages, as I said, in memory. We're going to use that active bit to tell us which pages are active. If a page is not active, we can feel free to send it out to disk. And of course, then we mark the page table entry as invalid and the bookkeeping bits to tell us where that page got stored on disk. Another example is, remember a fork. Right? When I do a fork, it's really fast, right? Because I don't actually copy all of the parent's address space and create a copy for the child. Instead, I just copy the page tables. So I copy all of the page tables, which is going to be much, much smaller, and I mark any entries that were read-write as read-only. So now what's going to happen? The program, the child or the parent is running along, and it goes to write something. It's going to generate a fault because I'm trying to write a page that's marked as read-only. Now I trap into the operating system looks at the page table entry and says, oh, I did a copy on write. So now what it'll do is it'll take that page and it'll clone it. Create two copies, one in the parent, one in the child, and mark both pages as writable, read-write, and then restart the instruction. So that's where copy and write comes from, because we're only going to copy the pages when the child or the parent actually tries to do a write to them. Right, everybody follow that? That's how we make fork really fast. Okay. Another example is allocating memory. So when I allocate memory to a process, I call malloc or I call sbreak to get more memory, I ask the operating system, give me some physical pages. And the operating system returns a set of physical pages. Now, if those pages were used by another application, the operating system has to zero out those pages. Why? Well, what if that was a sensitive server process, or it was the kernel using that physical memory? It might contain secrets or SSH keys or other sensitive information. And so the kernel always will give you a memory page that's been zeroed. But it's expensive to actually go through and zero 4,096 bytes and do that a lot. And so typically what the operating system does is it allocates the page table entries, and then in the background it's got a process that's running through and scrubbing empty pages and making sure they're zeroed. Then when you actually try to reference that page, it swaps in one of those zeroed pages. And that way you don't have to wait when you're allocating for zeroed pages to be created. They're allocated basically on demand. Or I should say assigned. They're allocated when you make your request, assigned actually on demand. Okay, how do we do sharing? Well, sharing is really easy, right? So here we have multi-level page tables. We can share at the granularity of an entire page table. Or we can share at the granularity of an individual page, or both. Right, so we get a lot more flexibility. So we can have the page tables associated with code, and those get shared across all of the processes running the same binary. Or pages assigned to libc, and all of those get mapped into every address space. So it makes it really efficient for us to do sharing between processes. So there was a question. So the physical page number is 20 bits. Yeah, so the actual physical page number, in this case, it was 20 bits. It'll depend on the machine architecture. 20 bits is not a lot of memory, and so as machines have gotten larger and larger, now you can have machines with a terabyte of memory. You need more physical bits. more physical page number bits. Okay, so summary for two-level paging is before we just had one table in the middle that kind of mapped any page on the left to any page on the right. Now we're going through a top-level page table and then going through a second-level page table. So you can see here, I've divided up our addresses into 3 fields. Right, so our lower 3 bits are our offset. Then our next 2 bits in green are our second-level table. And our 3 top bits are our top-level page table. So top-level page table has 8 entries. And then our middle tables here have 4. And then we have 8 bytes on each page. Yes? Yeah, so the question is the page table structure at the top level the same as the page table structure at the next level? Yeah, usually. It's the page table entries are the same at every level. And that's just because it's easiest to do that in hardware, to have uniformity. If you had 2 different types of page table structures, it would make for more complex hardware. Yes? The question is, if the operating system wants to modify a page table, does it do it in virtual address space or physical? It's in physical address space. So page tables are stored in physically addressed memory, but you could also store page tables in virtually addressed memory. But it depends on the machine architecture. Yes. Well, it's never, the kernel isn't doing the address translation, it's setting up the tables, and then the memory management unit in hardware is walking through the tables to actually do the translation for you. So operating system sets everything up and says, these are the rules, this is what these tables look like in terms of mapping from virtual to physical, and then the hardware actually implements walking through these tables so that it's fast. Mhm. Yeah, so the operating system can either generate translated addresses, but it can also, remember, I don't know where it is in my slides now, but we have 2 views, right? There we go, slide number 2. Right, so there's the CPU generating virtual addresses, but the kernel can generate untranslated addresses. So the kernel can actually say, I want to write this physical location of memory. Right, and it has to be able to do that because if it's going to pull a page in from disk and write it somewhere, it has to be able to access untranslated addresses also. Okay, question? So the question is, when I do a malloc, am I going to read a page or get a page that, if I read it, is going to have all zeros, or could it have random data on it? The answer, unfortunately, is yes. You could, if the page is freshly allocated by the kernel, get a page that is all zeros and has been zeroed out. If, however, you've done a bunch of mallocs and a bunch of frees and a bunch of mallocs, it depends on the implementation of malloc and whether you call something like zalloc, which will zero the page. When you do a free, it just puts the page or puts the memory back into the heap. It doesn't necessarily zero it out for you. So that's why there's a zalloc, I think it's called zalloc C library function, which gives you a zeroed out page. It guarantees the page is going to be zeroed. Okay. So here, if we want to grow the heap, add a new page to the heap, we simply just, or reference a page rather on the heap, we simply just look in the top level table. So this is going to be entry 100 in red. Then the next level is going to be 10. We look there, and that gives us this 10,000 in binary, which maps to right here, 80 hex. Right? So we just walk through our tables, and that tells us what the physical address is. Copy over the offset. So in the best case, right, the total size of the pages that our page table here is going to be proportional to the number of pages being used by the program's virtual address space. Right? That's much smaller than before, where it was proportional to the maximum size of the virtual address space. So assuming the programs are relatively small, it means our page tables are going to be relatively small. And for these second level tables, they can live out on disk if we're not using it. The price we pay now is just to do a memory read or write or instruction fetch. We're now going to do 2 additional memory reads. So we've effectively made our memory 3 times slower. And it's already expensive to go out to memory. Right? It's nanoseconds to access something on chip. It could be hundreds of nanoseconds to go out to memory. Now we've made that 3 times more expensive. And if some of these second level tables are living out on disk, that's going to make that even more expensive. So we're going to need a solution. And we'll come back to that in a moment. Okay, let's look at another approach. So that was a tree of tables. Instead, we can try and combine like the benefits we get from segments with the benefits we get from pages. So the lowest level is going to be a page table in any tree-oriented structure. Why? Because of really simple allocation, right? We don't have to worry about external fragmentation. If we put page tables at the top and segments at the bottom, we'd have to worry about moving these segments around in physical memory, finding large enough contiguous chunks of memory to be able to allocate those segments. So it's much better to use page tables at the lowest level. Okay, then we just use our bitmap. Higher levels could be segments. We could have any number of levels, but we'll make our top level in this case be a segment. So now our virtual address is going to look like this. At the top, we have a segment number, a virtual segment number, and then we have our virtual page number, and then we have our offset. Because our lowest level is paging, a page table, we can just copy the offset over. Fixed size pages. Our top level, we'll use a segment map that we store in the processor. So here we have 8 entries, base and limit, and those each point to a page table. And then we use our second level of our address, our virtual page table, of virtual page number rather, to index into that table to find the physical page number. And of course, as always, don't forget, we have to check to make sure we didn't run off the end of the table. We have to also check all of our permission bits to make sure there's no issues with the access mode. All right? Now, when we do a context switch, before, when we had a tree of tables, we just needed to save out that page table base pointer, or CR3 register. Now, it's just like with segments, we have to save out the segment map. Right? So it's a relatively small amount of data that we have to save on a context switch, on a context switch between 2 different address spaces, between 2 processes. Now, how can we do sharing? Well, we can share now at the level of a complete segment. So we just simply point to a page table representing the shared segment, like our shared code. Now, if we have another process B, it's just simply going to point to that same segment. It's going to have its segment point to that same shared segment page table. And now we have the same data that's visible in both programs. And again, if we're dealing with virtual addresses and references and things like that, or pointers, we're going to want to make sure that we put them into the same segment so that the virtual addresses are valid in both address spaces. If it's just a table of integers or other sorts of strings, then we don't have to put them in the same place. But if we want to have pointers or code or anything like that, they have to go into the same virtual segment. Okay. So let's take a step back and look at what we learned with multi-level translation techniques. So advantages. Well, we only are going to end up allocating as many page table entries as we need for our application's usage. Right? So if we have a really sparse address space, all that sparseness, it doesn't matter. Right? There's no data structures that we need to have to track that sparseness. Right? That'll all get captured in the top level of our data structure. Now, if we just allocate one page, kind of uniformly, throughout large gaps in the space, yes, then we'll end up with something that's not very sparse as a set of data structures. But that's not typically how we operate. We typically have like code, data, stack, and heap. And so those regions can be really far apart and won't take up that much space overall for our bookkeeping. We get easy memory allocation as long as we always use page tables at the lowest level. We can use a bitmap to do our allocation. We get easy sharing, right? We can share an individual set of pages, or we can share at the level of a page table or entire segment. So a lot of flexibility. But everything comes at a price, and so some of the disadvantages are we still have a pointer per page. Right? So for every 4 or 16 kilobytes of memory we want to allocate, we're going to have a page table entry. So that could be expensive. Oh, there was a question about what is the advantages of using segments and pages versus just using a multi-level page table. It's a design choice. So whether you choose to use multiple levels of page tables or you choose to use multiple levels of segments is really just an architectural design choice. When the architects are looking at what's the target market for this processor or architecture and how are people going to use it, they try to design a memory system that'll work well with both the applications and the operating systems. And so segments and page tables or multiple levels of page tables are just 2 examples of the approaches that people have taken. We're going to look at another example in just a moment. But they're all trying to accomplish the same basic idea. Okay, the other issue we have is that our page tables themselves, where they can be more than one page, have to be stored in contiguous memory. So that does lead to some potential external fragmentation issues, because if I have a page table that is 20 pages long, I need to find 20 contiguous runs of zeros in order to store that page table in memory. And so I might have to do some moving data around in order to make it work. But if I use for a 32-bit machine, if I use the 10, 10, 12, my page tables are 1 page, and I never will run into that kind of problem. So another disadvantage which we just saw is that I have to do multiple lookups in order to find each reference. So I have to walk through multiple page tables doing multiple memory references in order to do one reference to memory, a read, write, or load, instruction fetch rather. So that's going to be expensive. That tells us we can't, there's no way that it could be feasible for us to do translation, to actually do the full translation for every single memory reference. We're going to have to figure out a way of amortizing those costs across many memory references. Okay, so remember dual mode operation, right? Do we let the process access its translation table? No, right? Because otherwise it could access any memory. It could access memory associated with other processes, could access operating system code and data. The hardware gives us two modes of operation typically, a user mode and then a kernel mode or protected mode or supervisor mode or whatever you want to call it, but it's a special mode that has complete access. User mode is very restricted. Kernel mode, you can do anything. Now, some processors, like Intel processors, include multiple levels. So there's actually 4 different rings that you have that allow you to have different levels of access. So you have your supervisor or your protected mode that has the highest access, and then you have lower levels all the way down to user mode. And on x86, the level below, the highest privilege level, is typically used by hypervisors. Sometimes it's used by device drivers, so you can limit what they do and their ability to corrupt or cause problems for the operating system. Okay. Now, certain operations, again, with dual mode operation, we're going to restrict to being in kernel mode. So changing that CR3 register, changing the segment map, you can only do that in kernel mode. And that way we can guarantee that the user can't change what their translation mapping is. Okay, and also, there was a question about reading and writing the page table entries themselves. That has to be done when you're in kernel mode. You can't modify them or read them from user mode. Okay, so let's make it all real. So here is an example of x86, which combines both segments at the top level along with paging, a multi-level paging scheme. So it's taking everything and putting it all together. So you get the segment. So here we have a logical address, or virtual address, or what they call a far pointer. And it could either contain the segment, or the segment can come from the instruction itself. So here the segment comes from the instruction. It's the GS segment, and that's the segment selector. The segment selector selects a segment descriptor. We look it up in our global descriptor table. Right? That's global across all processes. There's also an LDT, or local descriptor table, which is specific to an individual process, and you can actually control which one the lookup happens in. Okay, and that is going to give us a base address here for a segment within our linear address space. So this is how we go from what they call their logical address to our actual address in our linear address space. That linear address is now what we're going to look up in our multi-level page table. So we're going to divide that linear address into a directory, a table, and an offset, and just do our walkthrough of those tables in order to actually get the physical address that we want. All right? So in most cases in x86, they just simply map this linear address space to be all of, in every segment to be from 0 to the top of memory, so they're not really using segments. They're just kind of ignoring it. And the addresses you're generating then are just going to be these linear addresses. Okay, so here's an example in x86 for 32-bit addresses. So here segments are either, again, implicit in the instruction, or they come from the, implicit in the instruction, or they come from the address. So there's 6 segment registers, stack segment, code segment, data segment, extra segment, and then F and G segments. And the segment register is just a pointer to this segment descriptor. So again, if we look back here, it's an index into this table, the global descriptor table, or an index into the local descriptor table. So local descriptor table is a per process segment map, you can kind of think of it as, and the global descriptor table is global. So for example, if I'd shared binaries, I would put those entries into the global descriptor table. So like for shared code. Then there's the current requester privilege level. And so this is what the actual descriptor looks like. It contains a lot of information. I'm not going to go through all of it. It tells you what kind of segment it is, whether it's a code, data, other segment, and that's important because code segments are execute only. What else is important? It tells you what privilege level is required to access it. You have to make sure that the requester privilege level is less than the actual segment level. That way, it guarantees that whether you can access it or not. So if it's kernel, you wouldn't be able to access it from user mode. And then there are extra bits that you can use for the operating system, the bits in A, and that's probably all that's really important. Okay. So let's say we wanted to be able to have a 48-bit virtual address space. Because on a 64-bit machine, I could potentially have really large pointers, like 64-bit pointers, or more commonly, you have something like a 48-bit pointer. So that I could do with a 4-level page table. Right? So I'm going to use the lower 12 bits for my offset. Now, because my page table entries are going to have to be bigger, because my physical addresses are going to end up being larger, now I'm going to have to go to 8-byte entries. So if I go to 8-byte entries and I have 4-kilobyte pages, how many entries do I have? $4,096 divided by 8. Powers of 2. 512, right? Half of 1024. Okay, how many bits do I need to index into a table with 512 entries? 9. It's right there on the slide too. But. Okay, so our page table pointer, our CR3 register, points to our base or our directory or whatever you want to call it. Each of these page table entries is 8 bytes in size. There's 512 of them. And I just simply go walking through all of these tables until I get the actual physical page number of the page that I want to reference. Combine that with my offset, my 12-bit offset, and now I have my physical address. Right? And so you can actually do this. Would you want to do this? Probably not. Right? Because for every memory reference, I'm doing 1, 2, 3, 4 just to get the address to then be able to do the 5th reference, which is actually going to be my instruction fetch, load, or store. All right? So not very efficient. Doable, but not efficient. So one thing the x86 supports, which kind of helps with some of this, is larger page sizes. Right? And so here's an example where you have 5 levels of paging. If instead I have pages that are 2 megabytes in size, right, now I need fewer levels. But why? And I can go even larger, right? I can have 1 gigabyte size pages. So when might I want to do that? Any ideas? What would be the benefit to having 1 gigabyte size pages? What would be an application? Let's see some creativity. Yeah. Yeah, exactly. Databases, right? If I have a database, I want to manage the objects in my database. I might want to keep a large blob in memory. And so having a 1 gigabyte page means that I could keep all of that in memory, right? And manage my access to it. Video would be another example. If I'm editing video, I might have very large video segments, and I can completely fill the pages. The key thing is thinking about applications where either for a 2 megabyte page size or a 1 gigabyte page size, I can completely fill the page. If I don't completely fill the page, if I put a 64 kilobyte stack on a 1 gigabyte page, then I have a lot of internal fragmentation. And I've just wasted my expensive memory. But if I have an application where I'm going to keep those pages full, then this makes it very efficient to have a large virtual address space and not have to do 5 memory references to do 1 read-write operation. Okay. So great for kernel. The kernel can all be in one page rather than in lots of pages. And it's great for large libraries and so on. Okay. What about 64-bit addresses on a 64-bit machine? I could just have a 6-level page table. No. That would be way too slow, right? Because we're going to have to walk through this page table, then this page table, and this page table, then this page table, then this page table, this page table, and then finally, we actually get to do our load and store on every single operation. So it would be just really inefficient. Okay, so an alternative is what's called, for not really good reasons, an inverted page table. You create something, a data structure, you get to name it. And people don't always pick the best names, let's just say. So the way to think about this, and why it's called an inverted page table, is if you think about what we've looked at so far, all of these, we kind of walk through the table. So it's a forward path that we take, mapping from our virtual address to our physical page number. And so the size of our page table is going to be proportional to the amount of virtual memory that we've allocated to this process when we use one of these multi-level schemes, so we don't have sparseness in our data structure. But the actual physical memory that we have could be much, much less, right? If you look at a 64-bit machine with 64-bit pointers, that's a much, much, much larger virtual address space than the actual physical space. A machine might only have 64 gigabytes of memory. And so we've got this huge data structure for our mapping, and the actual pages that are in memory is much, much smaller. Most of our code and data and everything might be living out on disk. So what we're going to use is a hash table. We're going to take our virtual page number and give it to this hash table. And it's going to give us back our physical page number. Now, it's called an inverted page table. The nice thing here is the size of this hash table is proportional to the size of physical memory. Because it's just keeping track of what's actually in physical memory and where is it. If it's not in the hash table, then we have to go look in our bookkeeping data structures to figure out, hey, where is it out on disk? So that's nice. The size is now independent of the virtual address space. It's proportional to the amount of physical memory that we have. And so it becomes a really nice solution to when we have a 64-bit address space, right? And we don't want to have 6 or 7 or whatever levels of our page table. So the downsides here is that hashing, it's hard to come up with good universal hashing functions that have short chains. Right? Chains are where you have a collision, you go and you look in the bucket, and it's not the item you look for, so you got to rehash and look in another bucket, rehash and look in another bucket. We don't want to do a lot of that because then that'll be really slow and expensive. So you want hashing functions that generate very short chains. And you're doing this typically in hardware. And so that makes it even harder to figure out what are good hash functions. The other issue you have is if I want to walk through the page table itself, there's no locality here, right? Because one virtual page number hashes to some location in the hash table. The next virtual page could hash to something far away. The next virtual page could hash to something far away. So there's no locality. Whereas with the approaches we were looking at before, one virtual page table entry was right next to the next entry, was right next to the next entry. And in fact, they all fit on one page. So it was very efficient. Okay, but the benefit here is the size of our hash table here is proportional to the number of pages being used in physical memory, which is going to be much, much smaller than the number of pages used in virtual memory. Okay, so I'm just going to end with the next slide. So we looked at a bunch of different translation approaches: simple segmentation, really fast context switching. I just save out the segment map. The disadvantage, we can end up with external fragmentation. Paging is nice at the single level because we have a uniform, rapid way of allocating memory, no external fragmentation rather, but we end up with table sizes that are proportional to our virtual address space and are mostly full of empty entries. So it doesn't work well for sparse address spaces. Page segmentation or multi-level paging, both of those approaches make the table size now proportional to the number of pages in use in virtual memory. We get the advantages of fast allocation by using paging at the lowest level. But the disadvantage is it can be multiple or many memory references just to do one read or one write. So we're going to have to fix that, and that's what we're going to fix in the next lecture. Inverted page tables, now we have a table size that is proportional to the number of pages in physical memory. But the downside is we have these hardware hash functions that could be super complex, and we don't have locality for our cache of page table entries. So on that, we'll continue on Thursday.